Hello everyone, I hope you're having a great SQL Saturday. I've seen the schedule, there's a lot of interesting sessions, so I hope you find the one that you are looking for. If you are looking for the intelligent query processing session, you are in the right place. That's my session. That's what we're going to talk about in the next hour. If that's not what you're looking for, this is a great time to go back to the schedule, verify which room you really want to go into. But you're more than welcome to stay. We're gonna do a lot of demos on the latest features for performance tuning on SQL Server 2019 and Azure SQL. So I'm just gonna give everyone a few minutes to settle down. Maybe grab your coffee or get comfortable or change room if you want to, but I really hope not. I hope you stay. Alright, so I think we can begin. Like I said, hello everyone. This is Intelligent Query Processing session for SQL Saturday Bangladesh. Before we start, I would like to thank the sponsors for the event, as well as the organizers. This is actually my first time speaking with the SQL Server user group at Bangladesh. So thanks for having me and thank you for choosing this session. Let me just introduce myself. I'm Pio Balistoy. I'm a Filipino Microsoft MVP data platform for data platform based in Singapore. I've been working with databases for more than 17 years now. I started with SQL Server 6.5 and I managed every version till Azure SQL. For the last 10 years, I've been a lead Microsoft data platform consultant for PTN Services. It's a managed services provider based in Canada. When I'm not busy with that, I help organize the SQL Pass Singapore chapter, and I do help out with the Philippine Data Platform Forum back in Manila. So if you are looking, if you want to look for me, if you want to ask something, you can go to the Facebook group for those two groups. I administer both groups, so I'll be there. And after this session, if you want to reach out, if you have any questions about SQL or SQL Server, or you just want to connect, you can reach out to me through those channels, or you can add me on LinkedIn. You can also check out my YouTube channel. That's the Singapore SQL Pass YouTube channel. Ever since the pandemic, most of our sessions have gone virtual. We also do data sessions, which happens every Tuesday. So if you like these kinds of content related to data platform, you can check out the channel, or better yet, you can join us since our time zone are almost the same. We do host it during Singapore evening, so if you want to join, you're more than welcome to. And I think that's enough about me. Today we're going to talk about the new features in SQL Server 2019 for performance tuning, specifically the intelligent query processing family. Alright, so this is the problem that we would like to address. The DBAs spend most of their time tuning database performance. And this is the same whether you're on-prem or in the cloud. More often than not, you get developers or application support telling you, hey, my query is running slow. This was fast yesterday or something. This is slow. So your DBA ends up troubleshooting, trying to find out why this query is slow, and then spending their time tuning these queries. And this takes away valuable time for your DBA to be doing something proactive for your environment. I'm not saying it's more important, but they could be doing a lot more than just tuning your database. And more often than not, these performance issues are query tuning issues. So let's take a look at what happens when you submit a query, and how does it really work in the back how does the process really work. And this is a very simplified version of how everything works. So if you want more information about it, you can go to the Microsoft Docs. So when you submit a query, it will go to the query parser. What it does is it checks your query and see if there's verify your syntax, and then translate your query into logical tree. Now, these even a simple query, it can be executed differently. There are different ways that it can be executed, different operations that it can use. So what happens then is this logical tree undergoes transformation to find out all the possible iteration of this query, all the possible plan on how this query can execute. Once it has those multiple plans, the cardinality estimation now checks these operations and checks the tables involved, and estimate how many rows you are going to use from this table for this operation, how many rows will flow from this table to the operation and to the next step, and it will do it for all the iteration of your plan. And once it has all the estimates, now it will try and cost each plan and identify which plan is the cheapest. And by cheapest, what we mean is the one with the least amount of compile time and execution time, balance between the two. So once it gets that the cheapest plan, it will then pin it to the cache, and then it will be available for that query and for any for a similar query that will run using the same query. Any transaction that will run using the same query. So once the query executes, it will check if it's previously executed, and then if it is, it will retrieve the cached plan, and then from the cache plan it can find out how the resources that it requires. So the requested memory, the requested number of memory, the will it run serially or parallel, would it need how many CPU. So all those information, it will get it from the plan, and then if the resources are available, then your query will execute. So that's how everything flows. So if you look at it, there's a few critical places where something can go wrong, or when something goes wrong on that pace, then everything is already very wrong. So if you take a look at here, if the row estimates on the cardinality estimation is wrong, then all the information, for example, whether it's gonna use serial or parallel, what type of operation it will use for this step, it will already be wrong because it might not be optimal for that number of rows. Just think about, for example, your cardinality estimation. Say for this table, you're only gonna select one row. That's the estimated number of rows you're going to use, and then it turns out the actual number of rows that you're gonna use from that table is more than 1 million. So if that happens, it already chose the wrong operation for it, and then if the operations are wrong and the estimates are wrong, the cost of that plan is more likely incorrect, and that means from the costing it will have chosen an inefficient plan, not the best plan for that query, and that plan is already cached on your memory. So when another query comes, it will still use the same bad plan. So when your plan is incorrect, when the estimation is incorrect, the costing is incorrect, the plan is incorrect, and then the resources that it requested may be more than what you need, or if that happens, then you're taking away resources for other queries, reducing the number of queries that can run at the same time given your resources. Or if you requested too little, then that means your operation will spill to somewhere else, like to the temp DB, which we all know sorting in the memory is a lot faster than sorting in the temp DB. So now that you have a temp DB spill, your query will run a lot slower than it's supposed to. So when that happens, your query execution suffer. So as you can see, this is a very critical point in the process. So let's take from there we can already identify a number of common reasons for a query to run slow. So what are the common performance issues for a query? First is missing statistics, uh, like if there's no statistics, then the cardinality estimation doesn't have any information. It will result into guessing the number of rows that it will use, and if it does, then the costing is already incorrect and the plan is already incorrect. Then you have a slow query. It can also happen that your query may have been correct. Maybe it's up to date 2-3 hours ago, 4 hours ago, but after that, a lot of transactions, a lot of changes happened on that table, and now your query is incorrect. It's already stale. So, for example, on your statistic, it still has one row, but you did the bulk insert, and there's already a million rows on that table. So the statistics is already too incorrect. And it can also happen that the sampling rate is inadequate. Now, this affects the histogram of your statistic, the distribution of your data. So if the sampling rate cannot get all the representation of your data, then the histogram will be incorrect, and then you'll end up with well, essentially an inadequate statistic. And this is that one or also ties into the next one. This one is a very common issue for a lot of queries and stored procedures. Bad parameter sniffing. For example, your SP, the parameter for your SP is part of the predicate of the query inside that stored procedure. So if certain parameters will change the behavior of the query, and then you run that first. For example, a certain parameter will return just maybe 5 rows, and that's the first execution of that SP. That plan will be pinned on your cache. But apparently there are other parameters that when you pass to that SP, now the query will return a million rows or 100,000 rows. 5 rows to 500,000 is very different. So the plan that is pinned on your cache is efficient for a query that will return a few rows. So the operations for that query is likely very different on what it really needs for a very large query. And you will end up with a very slow query. Another common problem is out of model constructs. This is essentially saying there's some outdated or anti-patterns for anti-pattern statement that can be written differently, or for example an inefficient estimate or costing for the engine that can be done differently, and we'll see that later on. So all these are very common issues, and they more often than not it's the same thing for a lot of queries. So wouldn't it be nice if this is something that your database can automatically identify and correct on its own without you having to change anything? And that's the improvement that we have for Azure SQL and SQL Server 2019. So there's a lot of new features, not just for 2019, even before 2017 and 2016. They introduced query store, automated tuning, and all these features allows you to improve your the query performance without you having to change the query itself, without you having to change anything on the application. If you take a look at it, it started around 2016, 2017, but actually, if you go back on 2014, for SQL Server 2014, they introduced a new cardinality estimator. It's the latest change for CE. The last change for the CE is around for SQL Server 2000. So that in itself already improved a lot. And then 2016 and 2017 came out, and there's a lot of new features. Query store, wherein now you have the capability to store the plans used for your query and track queries that are regressing. And then it also allows you to pin the plan. For example, you have queries with multiple plans and one is inefficient, one is better than the other. It gives you the capability to pin the correct plan. And then we have the adaptive query processing, wherein your query there's interleave and execution. Your query can have adaptive joins based on what's happening. And then they introduced something that is very game changing for the analytical workloads, the column store index. So all of these started from previous version 2016 and 2017. And then when 2019 came out, they wanted to add more types of these intelligent features. So, but they could not park it under adaptive query processing anymore, because it's not just adaptive joins. So they rebranded everything and called it intelligent query processing feature. Everything you see in blue were already out on 2017. Everything on green is the new features for 2019. So we won't be talking about the ones in blue, since they have been there. We are going to focus more on the ones in the green. We're gonna talk about each one of them, and we're gonna do a demo on how it affects your query and how it works. So if you can see here, memory grant feedback, for example, it has been available since 2017, but back then it's only for batch mode. So now that we have row mode, and then for 2019 we now have table variable deferred compilation. So this changes the way table variable behave. And then now we can do batch mode on row store for those analytical workloads on your OLTP databases. And then UDF inlining and approximate count listing, which is a whole different thing. We're gonna look at each of them one by one. And let's start with memory grant feedback. So memory grant feedback is a mechanism for SQL Server, wherein it can check your query operation if for the number of memory that you requested on your first run, and then it will check if you use that memory efficiently. If you're using that if the memory request that you asked for were used, for example, more than 50% of the memory you wasted. So that means you don't really need that much memory. So on your next run, it will adjust it. The memory grant feedback tells the SQL Server engine that, hey, this plan will ask for 100 gig, for example, 10 gig of memory, but it will only use 2 gig. Just give him 2 gig. That's what memory grant feedback is. Now, previously, memory grant feedback is only available for batch mode. What this means is you have to have a column store index on that table before you can use memory grant feedback. Now, for 2019, you can use it even for OLTP. And let's take a look at how it works so that we can understand it more and we can appreciate it more. Alright, so let's take a look. For all the demos for today, I'm gonna execute them first, and then I'm gonna explain while some of the queries are executing, because some of these will run a bit long since we're trying to demonstrate something for performance. So what we have here is Wide World Importers DW. It's a SQL Server 2019 server. So it's the sample database for SQL Server, but this one is an enlarged version. I ran a query earlier on to make the database larger so we can see the performance impact. We update the statistics for order history table and set it to row count is equal to 1. We want to simulate a skew statistics issue. Just a word of caution, never do that in production because that's going to be a huge headache. So we use wide world importers, and then we set the compatibility level to 150, which is 2019. all the features that we'll be talking about today are enabled by default on 2019. We just cleared the cache, so make sure that it's the first execution. So let's take a look. Here's the execution plan. Straight away you can see the warning sign on the hash match, and you can see why. Our operation is spilled into the temp DB because there wasn't enough memory requested. That means the transaction wrote, you can see here, it wrote 52,000 pages and read 52,000 pages on temp DB because the memory granted is just 1 gig. Yeah, so so that's a problem, because we all know that disk is much slower than memory. And if you take a look here for our select, the memory grant, it only asks for this one. That's all the memory it requested, because you can see here the CE estimated the number of rows for the table to just be just 1, but the actual number of rows is more than 3 million. So, but since we're in 2019, there are two new attributes for the plan. While we're doing that, I'm just gonna execute the query on another window because I don't want it to be kick out of the cache. Let me just do this one while I continue to explain on the other one. So yeah. So if you take a look here, we have two new attributes. You can only see this if you're on SQL Server Management Studio 17.9 and above. So there's an is memory grant feedback adjusted? No, because it's the first execution, we cleared the cache. So the last requested memory is also 0. So this is the first time that the engine encountered the query. So that's why it granted what it requested. It requested for 1 gig of memory, and it gave 1 gig of memory. All right, so look, it looks like it got kicked off the cache. So let's just wait for it. Yeah, there's still the problem. And if you look here, it's still 156, and it's a first execution because I'm using a smaller. Look at here. Now we execute it at once. After running it, we rerun the query, and it only took 3 seconds compared to the previous execution. And if you look at the plan, we don't have any spills now. And if you look at the memory grant info, see that now, because of the memory grant feedback, it knows that the last requested memory is not enough. Now it gives 625,000. So a lot more than what the previous request is. So, and you can see the parameter is now adjusting because it adjusted the memory for it. If we run it fast enough, looks like we're not fast enough. Oh yeah, you can see here. It still ran 3 seconds. We don't have any spills anymore. The one thing to show here, the estimated number of rows is still the same because memory grant feedback doesn't adjust the statistics. It just adjusts the amount of memory that it gives the query. So when you take a look at the memory grant info, it gave it the same amount of memory for the second run, and since the amount of memory it used from the previous run is the same as what it needs in this run, the status is now stable. Yes, stable, because the amount of memory it requires is the same. So if you execute it again and the memory requirement doesn't change, then it's gonna be perform the same way, 3 seconds. And when you go to no spills, and then yes, it's stable. It's still the same. It uses the same. The last requested memory is the same as the granted memory and the desired memory. So if you need more memory, it adjusts it for you. If there's a scenario wherein you requested for too much memory and you're not using it, memory grant feedback will also adjust it for you. And one thing that I failed to show earlier on. Remember, memory grant feedback has been there since 2017, but it's only for batch mode. Here we're on row store and execution mode is row, but memory grant feedback is now available for row store. Alright, so as you've seen, there's this is one of the new property for the plan is memory grant feedback adjusted. We saw some of the status that it can have. First execution is when it's the first time the query is executed. There's no cache plan for it. So first execution, the last requested memory is 0. Yes, adjusting, it will adjust the memory for you. It will release, for example, if you didn't use more than 50% of your requested memory, it will lower the request grant for you, the requested memory, so that you can have more resources for other queries. If it's less than, if you requested a lot less than what you used, then it will give you more memory as much as you previously used, so that your data won't spill to disk. So if you keep on executing the same query, if it keeps on seeing the same query, if it's still in the cache and the memory is no longer changing, then it will go to stable. That means it already allocated it the correct amount of memory. And then the last status is disabled, and this happens when the requested memory keeps on changing as you execute the query. That means if that happens, then it doesn't benefit from memory grant feedback. So what it does is it just disable MGF for that query, just for that query. So a few key points. For parameter sensitive query, it will not use MGF. As I mentioned, if the requested memory keeps on changing, it doesn't make sense to use MGF, because every time you run the plan, the amount of memory you will use is different. So it will disable the MGF. And the MGF information is stored in the cache plan. It's not persisted anywhere on the SQL Server, in the engine, or in MSDB or master. What that means is the information is only for plans that are cached in the memory. So if the plan is taken off the cache, then when you run the query again, it will be first execution again. All right, and then if, for example, you decide that MGF is not something that you would like to, certain queries that your workload doesn't benefit from MGF, there's a few ways of disabling it. One is the one we saw earlier, compatibility level. It's by default enabled for 150. So if you don't want to use it, just go down to 140. But that's a bit drastic, because that affects your whole database, the whole database. So all the features for 2019 will be disabled. So you can disable it by scope configuration, database scope configuration. If you just want to disable MGF itself, you can do it through that, or you can use it through hints. If, for example, you think some other queries on your workload will benefit from MGF, but there's a specific query that doesn't benefit from it, then you can use a hint for that query so that it won't use MGF. Now let's go to tabled variable deferred compilation. Now, so that's the definition. It uses the actual cardinality of the table variable encountered on the first compilation instead of a fixed guess. Now to understand this, let's go here. Now this is the legacy behavior. This is how table variables behave before 2019. Now, we're not here to debate which one is better, temporary tables or table variables. I just wanted to compare, to let you see the comparison between the two, so to understand why we need table variable deferred compilation. So for the traditional way of how it behaves, right? Temporary tables, you can create statistics for it. You can create indexes for it. You can create constraints for it, and it can create automatic stats. This improves the performance of the temporary tables. For table variables, you won't be able to do all that. For example, for index, you can only do inline indexes. For constraints, you can only do PK and unique constraints. And there's no stats for table variable. So what happens when you use these two for your query? During compilation, for temporary tables, it's deferred until the first execution of the statement. So during cardinality estimation, it won't say first how many is the estimated rows. It will execute the query first, and then it will defer compiling that table after the first execution, so that it has the correct estimate for the number of rows. For table variable, since it's a variable, the default guess, the compiler default its guess to 1. So when you use a table variable, it always during costing, during estimation, it will estimate the number of rows for that table to be 1. And this is okay for if you have less than 10 rows maybe, or you just have a few rows for your table variable. But if you have a huge table for your variable, then it becomes a problem, because now the query plan is the operations that it will choose is not optimal for a very large table. It will choose an execution plan for a single row execution. Alright, so let's take a look at deferred compilation for table variables. We are gonna change first the compatibility level to 140, so we can see how it looks like before. And then let me just execute this. So what we have here, see here, we're using the same database, wide world importers DW. We have a table variable orders, and then we insert the data from order history, and then select join that table variable to order history extended. So when we look at the execution plan, you can see here for the order variable, you can see the estimate is 1, but the actual number of rows is almost 500,000. So because of that information, the CE chose to do a nested loop. Now, nested loop is a very efficient operator when you have one side of the join, when you have a big table on one side of the join, and a few number of rows on the other side, or a single row, for example. What it does is it loops through the table with large number of rows, and just take the smaller number of rows and loop through the big table. And this is very efficient for small table, but when you have a very huge table on both sides, then it becomes problematic, because that's a very huge nest. It's gonna be a very long loop. Okay, so let's take a look. If we change the compatibility level to 150, so that we can defer the compilation for the table variable. So we're using the same select, using the same query. What we did is we just changed the compatibility level to 150, and then we clear the procedure cache. You can see straight away that it only took us 9 seconds. Yeah. So when we take a look at the execution plan, you can see how different it is. Table scan. For the table variable, you can see here, estimated number of rows is around 500,000. Actual number of rows, oops, sorry, let me do that again, is 500,000. So since the CE estimated it correctly, you can see that the operator used is not nested loop. Now it uses hash match, which is a more efficient operation for tables for joining two large tables. And you can see here, earlier we didn't the execution plan that didn't use any parallelism, but now since it knows how many the estimated number of rows is different, then the execution plan decided to do parallelism to improve the query time, and that's what we got. We got 9 seconds. That's how the deferred compilation for table variable helps us. So you see, table variable deferred compilation, as you saw on the demo, it helps improves the plan efficiency and the resource utilization of your query, and it helps with throughput, because if you conserve your resources, you got more resources to run parallel queries and other queries on your workload. Next, let's take a look at batch mode on row store. Batch mode was introduced in 2017, and it was closely tied to column store index, because it's more for analytical workload. But the problem is, in the real world, we do have databases that are we do run our analytical workloads on our OLTP database, and sometimes it's something that you cannot avoid. For example, if it's an IP, if it's an ISV that you cannot put a column store index on the table, you cannot change it, then you won't be able to use batch mode on this database. What batch mode is, it allows the operators for your query to process the data more efficiently by doing it in batch instead of doing it per row. So instead of processing one row at a time, it will process 900 rows, up to 900 rows instead of individual rows. This makes the operation faster, and this is critical and something that's very helpful for your analytical workload. Now that it's available for row store execution, now you can benefit from batch mode when you have mix OLTP and data warehouse workloads, like I mentioned before, or for tables that you cannot use column store index due to design limitation or vendor restrictions, because there's a lot of limitation for a column store. So if that's what's stopping you from using a column store on a certain table in your OLTP database that you primarily use for your data warehousing or reporting or your analytics workload, then this will help your queries a lot. Let's take a look at how it works in the demo. Let's just go here first. Let's try, we're gonna do 140 first, so that we can see how it looks like without before 2019. Remember, I mentioned that there's no batch mode on row store on 2017. It's only for batch mode is only for tables with column store index, so it's only for column store. if we do this select, so we set the compatibility level to 140, and then we'll take a look at how it looks like. I don't think we'll need this one, so let's put that away. So for 140, you can see here, storage is row store, execution is row. It took us 12 seconds. Now let's do 150. I cleared the cache so that it's not, we're not gonna blame cache if it's faster. So straight away you can see it only took us 5 seconds. And then when you look at the plan, you can see here storage is row store, but our execution mode is by batch, so it's a lot more faster than the previous execution, 5 seconds compared to 12 seconds. So that's batch mode over row store. Okay, so let's go back here. So some information on the heuristics for the row store. It will first do an initial check on the table sizes and operators used and estimate the cardinality. Now, remember earlier we said that we have, during your query, when we discuss how query works, it will undergo transformations so that it will produce multiple plans. So that on batch mode, on the heuristics for the row restore, it will checkpoint on the optimizer as it discovers new plans for that query, and then it will check if the plans if the cheaper plans make significant use of batch mode, then it will recommend batch mode for the plan. But if, for example, the optimizer sees that the cheaper plans doesn't use batch mode, then it will stop exploring batch mode alternatives and just go with row store, because from its point of view, you won't benefit anyway. It's the same performance with row store, so it will do row store for you. So, but if it benefits for batch store, then it will use batch mode. Now, having said that, the batch mode on row store doesn't guarantee that you have the same performance for the same table. For example, if this table has a column store index and it uses batch mode, it doesn't mean that the plan for that is the same as batch mode on row store. It's not guaranteed, and it's also the same. It's also the same with the compatibility level. Remember, we said this is available in 2019. What if, for example, we lower to 2017? If I got a row store a row store plan on 2019, will it be the same on 2017? It doesn't guarantee that. So it's something to keep in mind, just in case you're wondering why, or you compare the performance between the column store if you put a column store index on this table or not. All right, let's go to UDF inlining. So in UDF inlining, it converts your scalar UDF into equivalent inline query or subqueries that will result in performance gain for your query. To understand that, let's define first what scalar UDF is. I'm not sure. Probably most of you are familiar with it. Scalar UDF are functions that return single data value. Now, it's very great because you can create one UDF and you can reuse it for all of your queries that will use the same functionality, and it's modular. If you need to change it, you can change the UDF and you don't have to change all your queries. And then it allows you to have complex business logics and business rules, complex computations without having to write very complicated T-SQL query, since you are putting all the complications into the function. So you can build a more complex logic for your query. Now, it is bad because UDF are serial. It's you call, if you put it in your select query, it's iterative. It's invoked for every row, and since the complication and the complex logic is hidden within the UDF, there's no proper costing on the process that it requires, because when you do the costing, the UDF is not, if you put it on the select, right, it won't show what's inside the UDF. So the cost for that operation, for the UDF operation that will happen every row, is not included in your plan. Then once you open the plan, you won't be able to identify or understand what's happening, because the UDF is already all the complicated logic and process is hidden within your UDF. And like I mentioned, you cannot do parallel queries for UDF. It's all automatically gonna be serially executed. Now, right. So a few years ago, they had this white paper. They studied how UDF behave and analyzed the performance of it. And what the study found is that any complex UDF, any UDF can be converted into a very complex T-SQL subquery. And the interesting point that they found out is the performance of these complex queries is better than using the UDF. And that's what UDF inlining, the UDF scalar inlining does. Now, converting these queries into this, if you look at here, the imperative statement, these are the statements, for example, inside your T-SQL, inside your function, and then you can convert it into something like this, so into the relational expression in T-SQL. Now, it's a very complex process on how you can convert, and it's not a skill that you can easily pick up. So to help you, IQP is the one doing it for you. It helps you convert those UDF into a relational expression, so that it's easier it performs better than when inlining the UDF. Let's take a look at the demo so that we can see it in action. Alright, so let's take a look at UDF inlining. Now I'm gonna execute them first before I explain what's happening, just like for the others. Okay, so we have here wide worlds, the same database, wide world importers DW. We created a function called the UFN customer category, which accepts customer key. That function just gets the total amount, the total including the sum of the total including tax from order history, and does some categorize them based on that. So, and then here we made sure that the database is on 150, which is 2019. We cleared the cache so that there's no other information. Make sure it's for our run. And we use a different way of disabling the feature here. You can see here, I specifically use option to disable T-SQL scalar UDF inlining, because we want to see how it looks like before. So when you take a look here, it took us 52 seconds, and look at that. Wait, let me just pin this one. Sorry. So at first look, the execution plan looks very simple. No parallelism, nothing much here. If you're encountering an issue or a performance issue and you wanna tune your query, there's not much information here. There's nothing you can decipher from the execution plan. But take a look at this one. Take a look at the query stat for it. You see here, your UDF CPU time, your entire CPU time for the query is just used by your UDF. And from the query plan, there's no way for you to know why and how, or if there's any improvement that you can do. Now let's try and execute that with UDF inlining. Now, we are on compatibility level 150. We just turned it off earlier using this using the query hint. So now the query ran for just 12 seconds, which is a great improvement. And take a look at that. See how complicated the actual plan is. That's really what is happening on the covers. And you can see here it's stream aggregate, table history scan. And now you have a more holistic view of what's happening to your query. If you need to investigate, then it's going to be easier to pinpoint where the problem is. And it just ran faster. So, and now look at your query time stats. Now it's not hidden. It's not hidden on a UDF time. It's all for the query. So now if you want to tune it, if you want to take a look at what's happening, you will have a more you'll have a clearer view. Oh, something that I forgot. It's also here. If you want to find out if your query, if your function is inlineable, there is additional information in the SQL modules. You can see here there is a new property is inlineable. So if not all functions can be converted inline, so if it's inlineable, you can find it here. It is inlineable. If you want to know. Yeah. So let's go back to the slides. All right, and last but not the least, this one is a quick one because it's not really a function. It's a new aggregate. So approximate count distinct allows you to have an estimate of the count. I think everyone here has done a lot of select count asterisk for a table when they don't even really need the number of the actual number of rows for the table for that table. And this is a very common scenario, not just for the DBA side, but also for applications. There are dashboard applications that they don't really need the exact number of rows for that table. You just need a close estimate on how big it is for certain decisions. And this is very useful for analytics and for all your machine learning and AI stuff, because you don't really need, for example, if you're building an application for a train station and you need to have an approximate number of a close estimate number of people on the platform so that you'll know how many trains you're gonna dispatch. So count distinct is something that allows you to do that without lacking your table, without costing too much resources on getting the actual number of rows for that table. Like I said, a lot of DBAs usually do this when they are going to do something. They usually check how big the table first, how the number of rows. But in reality, we don't really need the exact number. We just need to know how big the table is so that we can formulate a plan on what we want to do. Now, approximate count listing solves that issue. It allows you to have a close estimate of the number of rows without the performance penalties of count. Yeah, so let's take a look at the demo for approximate count listing. Let's set the database compatibility level to 150, and then I think we can execute it at the same time. We can take a look. So yeah, according to the documentation for approximate count listing, the margin for error is less than 3%. So that's close enough if you're just using it to estimate how big the table is. So here we have the first one. We're using just count. So the actual count is 29 million. And then our approximate count listing gave us 30 million, which is pretty close. If you take a look at the execution plan, there's only, just to be clear, it's not like we have 1 million difference, because this one is 29,620,000. So, and this one is, it's just a few 100,000 rows. So if you take a look at the execution plan, you can see straight away that the count listing is more complicated. And then if you look here for the memory grant, take a look at this one. So for the count, we used up this much memory. What's that? 2,000. Yeah, that's very big. And take a look at this one. See that? Only 40. So that's what approximate count listing is. You reduce the usage for the resources, and you get a close approximate of the size of the number of rows for the table. Yeah, so that's approximate count listing. So it helps with queries that doesn't require exact count, and it reduces your resource utilization for count processes. In turn, it will increase your concurrency performance because it frees up more resources for other queries. And last but not the least, I think I already mentioned it during MG memory grant feedback, but all these features are enabled by default at compatibility 150. You can turn them off by lowering the compatibility level, but you lose all the benefits of 2019. You can disable them one by one, or enable them one by one using scope configuration. So, using scope configuration, you can disable or enable a specific feature if you think you can benefit with the other feature and just having issues with one. Or if you think only one query is affected that might not be benefiting for a specific feature for any reason, you can use the hint option on the query itself, so that only that query will not use this feature, and all the others will still be using it and benefit from it. And with that, all the demos, all the script, if you want to redo or you want to revisit, you can find it on IQP demos. All the information about IQP, you can find it on the docs page for it, aka MS IQP. Here's the link for the white paper. And if you have any questions for IQP, you can email the IQP team directly for feedback. With that, I would like to thank you for attending this session, and thank you for having me here. I hope you found something useful. If you have any questions, or if you wanna connect, like I mentioned when we started, you can reach out to me through all those social media channels. Thank you.